Hello. In this video, we'll be reviewing the basics of functions, including function notation, domain, and even how to combine different functions with basic operations. Let's get started. So to begin, remember that a function is just an equation representing different quantities. X values are your independent variables, Y values are your outputs or your dependent variables, which depend on your inputs, X. But the notation that we typically use to describe the relationship between these two variables is function notation. And we see in our box here that y equals f of x means that your output y depends on your input x. Literally, you're putting in inputs into a function's rule or equation to spit out an output y. So when we see f of x, we realize that your y value f depends on your x value. So for example, if we have the equation that f of x equals the square root of x squared plus x, we could then use function notation to find various outputs given a single input. So for example, if we're asked to find f parentheses 0, we would say f of 0. What that would be asking us to do is to find the function's output when we're inputting 0 for x. So basically, replace every x value with 0. Easy enough. We just get that the square root of 0 squared plus 0 gives me the output of the square root of, you got it, 0, because 0 squared is 0, adding 0 to 0 is still nothing. And square rooting 0 is just a boring 0. So if you input 0, the output is 0 into this function. What about f of negative 2? Go ahead and pause the video and try that on your own. What'd you get? Well, if you input negative 2, did you get negative 2 gets squared, and then you add the results of x, which is negative 2, meaning that your answer should have been the square root of, 4 plus a negative 2. Watch your signs carefully because a negative times a negative is a positive there. And you end up getting the square root of 2. Well done. Or approximately 1.41 if you were to use a calculator there. So when you input negative 2 into this function's equation, the output it gives you is the square root of 2. Now, the other two examples on this page involve more abstract situations. So instead of me giving you a numerical input like 0 or negative 2, I'm now giving you an abstract situation. For example, what is f of the opposite of x, f of negative x here? Well, the reason we would ask you to do something like that is if you were testing for symmetry, as we talked about in our previous videos. Remember that if you put in the opposite x values, but you have the exact same output, that was a symmetry across the y-axis, right? So we would have y-axis symmetry. On the other hand, if you put opposite x values in and received opposite y values, that was origin symmetry. So that would be the reasoning for why you would want to put in a negative x to check for symmetry. So let's do that here. Does this have symmetry, if you will? So f of negative x would really mean, in this situation, that I would be putting in negative x for every input x. So negative x gets squared in parentheses plus my negative x. And let's see what we get. Well, negative x times negative x is just a positive x squared. Good job. But then we're asked to add the opposite of x. So plus a negative is really just a minus, right? So minus x. And you could simply say that is the output. If you input negative x into this particular function, you get the result of square rooting x squared minus x. Okay. So what does that mean for symmetry, if you remember from our previous discussions? Well, if everything changed to the opposite, so let me take another color here. How about white? You might see that better. For example, originally we had the square root of x squared underneath. We still have the square root of x squared underneath. That part's the same. But notice that with x, it's now a negative x for the output under the radical, which means one piece has changed but not the other. So it's not the exact opposite, meaning we don't have origin symmetry. We don't have an odd function here. But we also don't have y-axis symmetry because it's not the exact same as the original. So we would simply say we have no symmetry here. Now, the other piece in this slide that is interesting, that might seem a little intimidating for you, is f of x plus h. What in the world is this? Well, this idea is, what if you were to incrementally add on some number to your input x? So maybe h is 2, maybe h is 5. What would the overall output effect be, right? And we're going to learn about how this actually shifts your graph to the left or to the right h units, depending on the sign of that number. Eventually we'll get there. But for now, this is setting us up for a discussion we'll be having in the rest of the video later on when we start finding something called the difference quotient, which has to do with slope. All right, so this will be an important part of that, which is why we're introducing it now. But the idea is the same. Anytime you have a new input in parentheses in function notation, that simply means what you need to do is replace every x in the function's equation with whatever that quantity is. Last time it was a number and then it was a negative x. This time it's two things. It's x plus h. So let's plug that in for x and see what our output would be. We would have parentheses x plus h squared under that radical, and then we would have plus parentheses x plus h again. So what is the result in this situation? Well, it turns out that if you were to actually FOIL, that's what you have to do when you have a binomial raised to a power, you multiply it by itself by FOILing, wouldn't you get x squared plus that middle term, 2xh, you can actually write it out yourself in FOIL if you need to, plus 2xh plus h squared plus x plus h, all under that radical. So this would be the expanded version of what's underneath that square root. X squared plus 2xh plus h squared plus x plus h. There are no like terms there, so you can't really consolidate anything any further. But that would be one way to write your output. Again, that will be step one in finding something called the difference quotient later today. So make sure you take time practicing how to find f of anything. F of a number, f of opposite x, f of x plus h. That skill of using function notation correctly will be really beneficial to you, not only in this video, but in future examples and future concepts we're building on. Okay, so once you feel like you're confident with function notation, join me in the next example here. Example 1 says, if f of x equals negative 2x squared plus x minus 1, could you find f of 0? How about f of negative 2? Or f of negative x? Or even f of x plus h? So it's like the last example. Again, I really encourage you to pause the video and try this one yourself and then come back and see how you did. So let's see how you did. When you tried to find f of 0, for example, did you end up with negative 1? Let's see. You did negative 2 times 0 squared plus 0 minus 1. Following your order of operations, you would do your parentheses first, but there's nothing to do inside. Then you would do your exponent, so 0 gets squared, which is still 0. Then you would multiply or divide. Well, here it's multiplication. 0 times negative 2 is just negative. Nope, sorry, I misspoke. It's just 0. And then plus 0 and minus 1, and that gives you your answer of negative 1. Now, a shortcut there is to recognize that anytime you have x to any power, if you're replacing the x values with 0, each of those terms disappears. And that's why I can simply look at that polynomial and know that the answer is negative 1. So that's a little shortcut. What about f of negative 2? That one takes a little more thinking, doesn't it? So you had to do negative 2 times the input of negative 2 to the second power plus the input again of negative 2 minus 1. So what was your output? Did you get the right answer? Let's take a look. So you first would have done negative 2 to the second power, which is 4. Then you would have multiplied negative 2 times 4. And then finally, you can add and subtract in any order from left to right. So that's actually negative 2 minus 1 is negative 3, if you combine those two. Finally, you get negative 8 when you multiply negative 2 times 4, minus 3. So if you have negative 8 and minus 3, that's like owing $8, and then you owe another 3, you owe $11. That's negative 11. You add the numbers and keep the sign negative. Okay, so we have f of negative 2 we found. And again, if you got one of those wrong, like the second one wrong, take a look at where you made your mistake. Because as humans, we tend to make the same mistakes over and over again. So if you can start rewiring your brain and how you approach those problems and do them correctly a few times in a row, you'll actually become skillful at this type of problem, okay? All right, the next one we have here is f of negative x. So for f of negative x, remember this is important when we're testing for symmetry. We're going to check whether or not we get the original, a mixture, or exactly the same when we put in the opposite input. So let's take a look at what this one gave us. Negative 2 times negative x to the second power plus negative x in parentheses minus 1. In this case, negative x gets squared, so that's a positive x squared. So that part's positive. So we really get negative 2 next to x squared, or negative 2x squared. Then we have a positive and a negative next to each other, so that's just a negative result, negative x, minus 1. So that would be our answer. That's the new output we get when we replace every input, x, with a negative x. What does that mean as far as symmetry is concerned, if you're curious? Well, the first term stayed identical to how it started. It's still negative 2x squared. But the second term switched, didn't it? So that one became negative when it had started off positive. So already when you have a mixture like this, you know that there is no y-axis nor origin symmetry because it's not the exact opposite, everything didn't change, and it's not the exact same thing as we started with. You also know that -1 stayed the way it was. So this is definitely a mixture of staying the same and changing. That's going to have no symmetry. Okay, last one. This will set us up for that difference quotient later today in the video. F of x plus h. This is probably the one that caused you the most headaches. Okay, let's see how you did. You would have taken -2 times parentheses x plus h, all to the second power, plus parentheses x plus h minus 1. Then what did you do? That's right, you have to do that exponent first. Good job. Notice some students, I'm not saying this was you, but some students would be tempted to distribute the -2 first. Why can't you do that? Order of operations, that's right. I have to do my exponents before I multiply, and distributing there is multiplication. Okay, so let's continue the correct way that we've agreed upon. -2 would get multiplied by the result of foiling x plus h times x plus h. You do enough of those, you'll know exactly what this looks like. X squared plus 2 copies of xh, good job, plus h squared, because you end up with xh 2 times. Plus, notice that that's a plus sign before the x plus h in parentheses. If it had been a minus sign, you would distribute the negative, but a positive in front just means that each term is still positive. Positive x and positive h, no longer need to write those parentheses. Final answer, you would distribute and combine like terms. And let's see what you got. -2 gets distributed, so you get -2x squared. That's the only term like it. -2 times 2xh is -4xh. -2 times h squared is -2h squared. I'm running out of space, so I'll circle down here. Plus each of these 3 terms, so plus x, plus h, and minus 1. So in reality, there's 6 terms it looks like for this output. -2x squared minus 4xh minus 2h squared plus x minus h minus 1 would represent the entire output when you change the input by adding an h to the x value. Okay, again, that'll be really important as we build and get ready for the difference quotient. So make sure you really practice function notation before you go on to future concepts in this video. Okay, take a look at our second concept in this video, and that is how do we find restrictions on the domain of a function? So what was domain again? It was just the set of all potential inputs which are allowed. Okay, so what x values are allowed to be inputted into the function's equation. You might be thinking, couldn't I put any number or any letter? Maybe, but there are a couple of restrictions that you've seen before that I want to remind you of. The first one is a fraction. We call those rational expressions or rational functions. Now, whenever you have a fraction, there's one rule that you have to follow, and that is there's a certain number you can never divide by. Do you remember what that number is? It's 0, right? In fact, if you have like an iPhone, you can actually ask Siri, Siri, can I divide by 0? And she'll tell you a really funny answer. So I would check it out if you have that. Okay, so as far as dividing by 0, completely not allowed. So that means we need to restrict any potential inputs which would make our denominators equal to 0. So anytime I have a fraction, I'm simply going to say my denominator is not allowed to equal 0. So that would mean solve that potential inequality for the x values which are problematic, and then restrict them from the domain. So for example, if you got something like x can never be 2 because 2 would make my denominator 0 in this situation. What would you say then? Well, you could be any number less than 2 or any number bigger than 2, but you couldn't be 2. And that's why this expression would be how we define our domain. Negative infinity until -2 with a parentheses, meaning you don't include that number 2 or -2, whatever it is. U for union, meaning or any number that is bigger than that number, let's say 2. And so you would say parentheses 2 to infinity if that was the number that was in our restricted space for domain. Now, the second condition that you'll need to be aware of involves square roots, or really any root where there's an index of 2, 4, 6, any even index. Typically in your class, it'll just be square roots, but it could be any even index. Because remember, if you have a negative under a square root or a fourth root, that is imaginary. It cannot happen, okay? Because you can't multiply a negative times a negative and get a negative, or a positive times a positive and get a negative, or any sort of thing where they're like signs, they always produce positive results. So it wouldn't make sense, thus we call it imaginary. So what do we do instead? Well, we make a restriction on our inputs. We say that the radicand, anything underneath the square root, has to be non-negative, meaning it can be 0 or higher, greater than or equal to 0. So notice the restriction's a little bit different. The first restriction, denominators cannot equal 0. The second restriction, radicands are non-negative. They're greater than or equal to 0. So what would that mean? Well, what if you got a number like x has to be greater than or equal to 4? Okay, the one way you could write that then would be bracket 4 comma infinity. So starting at 4 or higher. Or what if you found that x had to be less than or equal to negative 3? Well, then it would be negative infinity until negative 3 with a bracket. Okay, so brackets again meant inclusion. I put a little note in the box here that if you are solving for one of those inequalities, be sure that anytime that you multiply or divide by a negative, you flip the arrow direction, okay, because that has changed the actual procedure. So take a look at this example. Suppose that f of x excuse me, equals negative 2x squared plus x minus 1. Now, this is a special type of function. We'd call this a polynomial because it has no restrictions on the domain, meaning it has no denominators, it has no radicals, and also it is a polynomial because all of the exponents are nice whole numbers. We'll talk more about that in the future. But notice, because there are no fractions and because there are no square roots, I could say that the domain appears to be all real numbers, any input. So negative infinity to infinity. And this works anytime you have a polynomial. We'll talk more about those in future videos. Okay? But basically, if there's no denominator, there's no square root, there's no restriction on the domain. Any input is allowed. You can see that on the graph as well if you click on the Desmos link. This is actually a parabola that opens down, hitting every single x value eventually as you go to the left and the right forever. What about the function, however, g of x equals 2x as your numerator divided by x squared minus 4? Would that have any domain restrictions for this function? Again, feel free to check out the Desmos link that I provided in the notes, and you can see that this graph has some really funky properties. In fact, it appears to split apart at a certain x value or 2. So why is that? Well, this particular function has a fraction in it, doesn't it? So that would mean that denominators have potential for problems, don't they? They could turn out to be 0 somehow. So what I would have had to do is say my denominator is not ever allowed to equal 0. Otherwise, it would be an undefined function. The output would not make any sense. So what would I need to do? I would need to take that denominator, which is x squared minus 4, and say it's not allowed to equal 0. It can't equal 0. So equal sign with a line through it. It cannot equal 0. What does that mean? Well, you could solve this inequality by either factoring, that's a difference of two squares, x plus 2, x minus 2, and saying that neither one of them can equal 0. So in the end, x can't be negative 2 or positive 2. Or most students would do the square root method to solve that quadratic inequality. So x squared could not equal 4, which would mean that if you take the square root, you got to be careful though, plus or minus, x could not be positive or negative 2. Because both positive and negative 2 create 4 when you square it, right? And 4 minus 4 gives you 0 in your denominator. So what does that mean as far as domain is concerned? Well, that goes back up to this first principle here. The domain for this function, for g of x, would be any number to the left of negative 2, so negative infinity until negative 2 with the parentheses, or any number between negative 2 and positive 2, so negative infinity until, sorry, I shouldn't say negative infinity, negative 2 I should say. Where's my eraser? There he goes. Pick him. There you go. Sorry about that. Went too fast for my own good. So negative 2 until positive 2, that would be the numbers between them, all right? What other numbers are allowed? Any number bigger than 2. Good job. 2 to infinity. So this would be the set of all potential inputs that are legal. Numbers which are less than negative 2, numbers which are between negative 2 and positive 2, and numbers to the right of positive 2. In fact, if you check out that Desmos graph, you'll see that's exactly what happens. So the only numbers which are not allowed are negative 2 and positive 2, and we've indicated that using the parentheses appropriately. That's where the graph splits apart because it wouldn't make any sense. It would be undefined. Okay, let's try finding domain ourselves in the next example. Again, study this slide, review it as much as you need to, and then try the examples on your own. So let's take a look. In example 2, it says, find the domain of the function below. H of x, so that's just the function's name, equals your input x divided by the square root of that input x minus 2. So x over the square root of x minus 2. Now for domain, what were the two restrictions that we're on the lookout for? Denominator. So denominators can never equal 0. That's true. And what was the second restriction? Yeah, radicals. Good job. Radicals can never be negative. So we would say that the radicand which in this case is x minus 2, must be what? Non-negative. That's right, greater than or equal to 0. That came from the radical. So when we have square roots, fourth roots, sixth roots, any sort of even index radical, that restriction applies. So first of all, for the denominator not equaling 0, the entire denominator was the square root of x minus 2, and it's not allowed to end up being 0. So this is a square root equation, really an inequality because of the not equal. But typically with a square root equation, you would simply get rid of the radical by raising both sides to the power of the index. So in this case, we would have raised both sides to what power? Yep, the second power. Good job. So if you squared both sides, that lifts that radical, leaving you with what's underneath the radicand, x minus 2. So x minus 2 cannot equal 0 squared, which is 0, which means getting x by itself, that x could never equal 2. So now we know on the number line, for example, if you were thinking of all inputs which are allowed, at 2 itself, we're not allowed to exist. So right now you might think, oh, that's just like an open circle, or maybe that's a parentheses, so something like this is going on. Anything to the left of 2 is okay right now. Anything to the right of 2 is okay right now. Right? Those are all your values that are allowed, but 2 itself excluded, right? So negative infinity to 2, okay. 2 to infinity, okay, but not 2 itself. But then we have one other restriction that comes from the square root, the radical, and that was that you can't have a negative under the square root. So you would say that x minus 2, the radicand, had to be greater than or equal to 0. Well, solving that inequality for x, since it's linear, you just get x by itself by adding 2 to both sides. So x must have been greater than or equal to 2. So now let's take a look at what that's saying. For this solution, we're saying at 2, you're allowed to exist because it's equal to, so that would be a bracket, and you're allowed to be bigger than 2. So bracket 2 to the right forever. Okay, so let's think about this almost kind of like you have two different parents to please, right? Two different restrictions. One parent says you need to be home by 10 o'clock. The other parent says you need to be home by 8 o'clock. So what do you have to do if you're trying to actually follow both of them? You have to go with the strictest interpretation, don't you? So that's what we're going to do here. We have two different restrictions, but we have to satisfy them both. So we're going to take the strictest interpretation of both of them. Okay, I know you probably would just try to get away with the easier one, but in this case, in math, we have to actually follow all the restrictions in order to make sense of anything. Okay, so the restrictions in the first case were we can't be 2. The restrictions in the second case were 2 or higher. So putting those together, where are we? Well, if you can't be 2, or you're 2 or higher, you must just be higher than 2, right? So putting those two together, our final answer would be, putting these two together, that you can't be 2 and you're greater than or equal to 2, that would just mean that x must be greater than 2. In other words, to write this in interval notation, that would be parentheses 2 toward infinity. So any number bigger than 2 would satisfy both restrictions at the same time. And you can test that. Put in the number 3, put in the number 4, put in the number 5, they'll all work. But if you start putting in 2 itself, what's the problem? Well, 2 itself would make 2 minus 2 under the square root, which is fine for square roots because the square root of 0 is 0, no problem. But then you'd have 0 as your denominator, and that would be problematic for the fraction itself. It would be undefined. You can't divide by 0. That's why we have to start at numbers bigger than 2. So 2.1 is okay, but 2 is not. Hopefully that makes sense, but I have a feeling a lot of you are scratching your heads and needing to review at this point, so feel free to do that before you move on to our last concept in the video. I should say 2 more concepts. This is a long one. Okay, so the next concept in the video is one that is absolutely essential for those of you who are going on in math, especially pre-calculus and calculus. It's called the difference quotient. Now, before we get into it, you can just memorize it if you're stopping in this class, but I will tell you, for those of you going on, it's basically the slope formula, right? So what do I mean by that? Well, suppose you have a function, and this function is called f of x, and you pick 2 points. So we've done that in this picture here. We picked a point on the green function, if you can see that, hopefully. If not, it's a parabola, okay? So we've picked up 2 points. I'll try to draw it better so you can see it, in case your colors aren't showing there, I'm not sure. Okay, so you've picked this function, 2 points on this function. So I picked a point x and a point a little bit to the right of x. So if this is like x, a little bit to the right of x, we're going to call it x plus h. What is that saying? Well, it's basically telling us if we pick 2 generalized points, x and x plus h, then they're going to have generalized y values. The output for the function at x would be called f of x. And so that's right here, f of x at this output. That's f of x. On the other hand, the output for the input x plus h would simply be f of x plus h. So that's going to be whatever this value is right here. That's f of x plus h. So you have two x values and you have two y values. You could find the slope between 2 points, couldn't you? That's true, right? Slope is simply rise over run, or y2 minus y1 over x2 minus x1. And that's what we've done here. If you look at the second output for y, wouldn't it be f of x plus h? That's the higher output. Minus the first output for y, wouldn't that be f of x? That's what we have here. So that's basically your y2 minus your y1. And then for your x2 minus your x1, that would really be x plus h minus x. So what would happen if you took x plus h, that's like your x2, minus x? What would you get? The x values cancel, and you just get h. And that's how we get the difference quotient. Again, for those of you who aren't going on in math, if this is your last math class and you just are going to need to know it for the test, just memorize it. But for those of you who plan to go on, it is imperative that you understand what's going on here. Because what will be happening is we're going to let h get smaller and smaller and smaller as you get into calculus. And that will be how you'll find the instantaneous rate of change rather than your average rate of change. The difference basically here will be if you were driving your car and you're speeding, they could either clock you at 1 mile marker and another and find the average speed that you were going and give you a ticket based on that. Or they could use a radar gun and find the instantaneous speed that you were going. Okay, that would be what this difference quotient gives them the power to do mathematically. So the difference quotient will allow us to get instantaneous rates of change in calculus. But for now, you need to memorize it, basically. The formula is f of x plus h minus f of x, all divided by h. Let's practice how to do it in practice here. That was the concept, here's the practice. Suppose we have a nice linear function. F of x equals negative 3x plus 1. So it's a line because the highest power is a 1. How would I find the difference quotient here? So I'll walk you through this one and then you can try the next one on your own. You would start off with f of x plus h. So you take f of x plus h. Whatever that is, you're then going to subtract f of x because those are your two y values. The denominator, remember, you're really taking x plus h minus the x, which gives you just h. Okay? So let's begin our difference quotient by writing down the formula correctly, and now let's apply it. So what did we do here? Well, to get this one correct, you would need to first find f of x plus h, which meant, what again? We've done it in our previous example, the first example today. That's right, we replace every x with x plus h. So replace your input with the input x plus h. This would make our function at this input negative 3 times x plus h, so I'm replacing x with x plus h, plus 1. So that's the result of plugging in x plus h for my inputs x. Sometimes you'll have multiple places where you see x, so multiple times you'll have to insert that. So be very careful when you're plugging in those values. Next, we're supposed to simply subtract f of x. So let's do that. What is f of x? Well, that's my original output, negative 3x plus 1. Negative 3 times my input, add 1. So let's do that. But notice the subtraction sign. We have to subtract whatever f of x was. But f of x was negative 3x plus 1. Now, some of you can do that in your head very easily. So you just take the opposite of the signs, right? Positive 3x now. So this becomes a positive 3x when you distribute, and a negative 1. If you can do that in your head and save a step, feel free. But a lot of students need to write that out. All divided by h. Okay, last couple steps are basic algebra. Can you distribute, combine like terms, and simplify? See how you do. Negative 3 times x is negative 3x. Negative 3 times h is negative 3h plus 1. And then after distributing the negative to f of x, you ended up getting positive 3x and a negative 1 all over h. Now, what should end up happening each time you do a difference quotient problem, lots of things should cancel now, okay? So let's take a look. What canceled? The negative 3x and the positive 3x. Yep, death to you, death to you. The positive 1 and the negative 1. Death to you, death to you. What's left there? Just negative 3h divided by h. Well, if they both have an h in common, doesn't that just mean that they cancel out? So I have negative 3. Now be careful. Sometimes you'll have 2 terms or 3 terms on top. Be sure that you divide h into each of them, not just one of them. Otherwise, you haven't fully done the operation. So in this case, what's really kind of boring, but it was an easier example, so I want to start with an easy one, is that I knew this already. Not just because I've been doing this for years, right? I knew this already because this was a linear equation, right? Linear equations are lines. meaning that they have a constant rate of change. And that constant rate of change starts with an S. It's called the slope. What is the slope of this line just by looking at the equation? It's -3, of course. Y equals mx plus b. So I already could have known that the rate of change was constantly -3, going down 3 units, right 1 unit, down 3 units, right 1 unit. So I didn't need the difference quotient for this particular function's trajectory. But when they get into things that are nonlinear, like parabolas or snakes or other functions, that's when the difference quotient is most useful. But the reason I showed you this one is I didn't want you to suffer too much right away. All right, so let's take a look at the next example, which is a little more painful, but gives you good practice. It says, can you find the difference quotient for the function below? F of x equals 3x squared plus 4. So this is an example of a nonlinear function, right? This is called a parabola, okay? So see if you can pause the video, go back to the last slide, and try it on your own and come back and see how you did. So as soon as you said difference quotient, what was that again? DQ, not Dairy Queen, difference quotient, what was that? Okay, that was the f of x plus h, minus f of x all over just h. Okay, the denominator's easiest part. So what was the f of x plus h part? That's when I replaced every x in my function with the input x plus h. So did you get, for this part, 3 times parentheses, x plus h squared plus 4? Now, a lot of students here wonder, why did she just write plus 4? If that's you, it's okay. Don't be embarrassed. The reason there's a plus 4 is the entire function's equation says, here's what you do to get your output. You take your input, x, you square it, you multiply it by 3, and then you add 4. That's what the equation's rule is, right? Now that we've changed the input from just x to x plus h, we still have to follow the entire instructions, right? We still have to square the input, so that's why x plus h gets squared. We still have to multiply that result by 3 and add 4, right? We can't just forget about the 4. We have to follow the rule that we've agreed to, the output that we've agreed to. Okay, so that is the result of f of x plus h. The next piece was, now subtract f of x. So minus the original function's output, which would have been parentheses 3x squared plus 4. I really encourage you to write parentheses around f of x because sometimes it'll be a negative sign as that first term and you'll have to distribute. Other times it's just a good reminder that you're distributing that sign change. All divided by h, that's exactly right. So let's see how you did. X plus h, did you square that first? So when you squared x plus h, we've done that a few times today now, did you get x squared plus 2xh plus h squared? Well done if you did. If not, find out where you made your error. And then you still have that plus 4 hanging around. What next? Well, next you would have distributed, right? The negative sign to both 3x squared and to positive 4, meaning you got the result, I hope, of negative 3x squared minus 4 all over your denominator h. Couple more steps and you were done. What'd you do? That's right, you distributed and combined like terms. The 3 got distributed and you get 3x squared. Careful with the multiplication here. That's plus 6x. Let's see, did I forget an h somewhere? Yeah, I did. That's an h right there. 6xh, I should say, plus 3h squared. So if you saw an h missing there, you were not incorrect. Your professor just forgot to write it. 3h squared. And then we have next to it, some things have canceled, haven't they? Yep, the 4s are dead. Death to you, death to you. And we just have the negative 3x squared all over h. Now, does anything else cancel here? Yeah, they do. The x squared terms, right? 3x squared terms. So this 3x squared term minus this 3x squared term, they cancel out. And here's one of those examples I was mentioning earlier that happens sometimes, right? Where you have 2 terms remaining that both involve an h and an h in the denominator. There's 2 ways to attack this correctly, and one, of course, that is incorrect. The incorrect one is simply divide through by h 1 time. That would be incorrect because you haven't divided it into everything in the numerator, right? So the correct way is either to remember to divide it into each of them so that your answer would be 6x plus 3h. That is the correct answer, by the way. Or you can simply factor out the h that's in common for both terms in the numerator and then cancel. That's probably the safer option for most of you. So if you had simply written this as h times 6x plus 3h all over h, then you can cancel with confidence that you didn't miss anything, okay? So it's still 6x plus 3h as your final answer. Now this will be important again in calculus because what this will tell you is at any x value in time, if x is like 1 second, 2 seconds, 3 seconds, or maybe a distance, you now know exactly how fast you're going at that time marker. H will again become 0 because it'll get smaller and smaller, so that'll become more irrelevant, okay? So for example, if h approached 0 here, 2 minutes after you started your trajectory, for example, you're going 12 meters per whatever it is, maybe seconds, so 12 meters per second. It's going to be telling you how fast you're going at that particular point in time. So it's very important as we move on in math. So difference quotient, that will take some getting used to. I've given you a linear and a parabolic example here, but they get more complicated as you move along. So take your time with them. All right, now the last thing I want to talk to you about in this very long video now, hopefully you've taken breaks and practiced, is how we can combine functions, okay? There's 4 basic operations like a 4-function calculator. There's addition, subtraction, multiplication, and division. Those are your 4 basic operations. So similarly, can you take those 4 operations and use them when you're talking about functions? Yeah, it turns out you can take a function f and you can take a function g, 2 different equations, and you can combine them using addition, subtraction, multiplication, and division. So I just wanted to go quickly over what that looks like with symbols real fast. I won't go through all these details. There's a lot on this slide you can take time with on your own. But what I wanted to point out here was when you take a look at something like parentheses f plus g of x, what is that saying to us? Well, that's saying take your f of x function and add it to your g of x function. So for example, let's say that in this example here, f of x is equal to x plus 2. So it's a nice linear equation. And let's say that they give you g of x is another linear equation. It's 5x minus 4. So that looks like what they've given us in this example here, okay? In this situation, if they asked you to find f plus g, what you would do is simply take f of x, which was x plus 2, and add it to g of x, which is 5x minus 4. How do you add those terms? Well, simply add like terms. 1x plus 5x is 6x, 2 minus 4 is negative 2. The things that students usually mess up, though, is with subtraction, not addition. Because notice here when I have f minus g, now I have to actually take f of x, which is still x plus 2, and subtract g of x, which was 5x minus 4. And what that would mean is I'd have to change my signs. So this would become x plus 2 minus 5x plus 4. That last plus 4 is usually the mistake students make. So make sure if you're prone to make that mistake, you make a note and start retraining yourself correctly. And so you're getting a new function there. Notice you got a function this time with a negative slope of negative 4 there. So you got a brand new result. The last 2 are also the same idea, right? Take your 2 functions and perform the operation correctly. What does multiplication look like? It looks like taking f of x, which is x plus 2, and multiplying it by g of x, which was 5x minus 4, and by FOILing, you'll get the result 5x squared plus 6x minus 8. So what ended up happening, if you're curious there, is when you multiplied the outputs of a linear function, a line, with the outputs of another linear function, another line, the new output function you got was a parabola, okay? X squared instead of just x. One more thing here. You'll see at the top of this slide, it says be careful to address the domain of the new functions that you've created. So that's that blank there if you're wondering if I forgot about it, right? What do we mean by that? Well, domain restrictions happen when we have a square root, right? Those can't be negative underneath. And when we have a denominator for a fraction, which can never equal 0. So when we have this function here, f over g, f divided by g, we're being really told to divide the f function by the g function. So in this case, that would mean x plus 2 is divided by 5x minus 4, and that's how we get our new output, our new function. But notice here there is a new restriction. In each of the previous cases, the domains would be unchanged, right? Those are all polynomials. There's no fraction. There's no radical. So each of those domains is just negative infinity to infinity. But what happens in this situation is that we would have a restriction. 5x minus 4, our denominator, cannot equal 0, which would mean that 5x cannot equal 4. In other words, x cannot equal 4 over 5. X can't be 4/5. So our denominator would be anything left of 4/5, anything right of 4/5, but not 4/5 itself. And you can check out desmos.com if you want to see the graph of that. Okay, let's do one more example, and I promise we'll call this video finished. So if we're given a function f of x equals 3x minus 2, and another function g of x equals 2x plus 1, how can we combine these 2 functions and also address their domains. So for example, the first case, they'd like you to find f plus g, and then f minus g, and then f times g, and then f over g. So this is a great example. It's a lot easier than what we've done earlier today, to take a time and pause it and try it yourself and build some confidence here. So for f plus g, what did you do? Well, you would have taken your f function, 3x minus 2, and simply add it to your g function, 2x plus 1. So this would have been 3x minus 2 plus parentheses 2x plus 1. So when you combine those like terms, did you end up getting 3x plus 2x, which is 5x, and negative 2 plus 1, which is negative 1, so that your new function is the line 5x minus 1 for your outputs? Good job. And your domain is still negative infinity to infinity, since this is still a line, a polynomial, right? There's no reason for a restriction on the domain. What about f minus g? What did you get there? Yep, you would have taken your f function, 3x minus 2, but this time you would have subtracted your g function, because that's the order it went in. So 2x plus 1 gets subtracted. What happened next? Well, you had 3x minus 2, but after changing those signs, because of the minus sign, you'd get negative 2x and a negative 1. Check out that last term. Is it negative? Is that what you wrote down? A lot of people write positive there incorrectly. What does that mean for us? Well, our final function then here would simply be what? 3x minus 2x is 1x, and negative 2 minus 1 is negative 3. So we get a new linear function of x minus 3. It's still a line, but it has a slightly different slope than we started. The domain for a linear function is still negative infinity to infinity. There's no restrictions present. But what about when you multiply the two functions? Did things get a little more intense? Yep, f of x was 3x minus 2 in parentheses, and we were told to multiply it by g of x. So that was parentheses 2x plus 1. And when you did that, you'd have to have FOILed, right? So what did you get? Well, 3x times 2x should have given you 6x to the second power. Watch out there. 3x times 1 is positive 3x, and negative 2 times 2x is negative 4x. So some students will do that part in their head and combine them and get negative 1x. That's correct. And then finally, negative 2 times positive 1 is negative 2. So the resulting function was actually a parabola, 6x squared minus 1x, or just negative x, minus 2. There's our new parabola. Again, if it's a parabola, it's really a polynomial, so there are no domain restrictions again, still negative infinity to infinity. The last one that might give you some restrictions is going to be f over g, right? And for f over g, you took your f function, 3x minus 2, and you divided it by your g function, 2x plus 1. Now, note of cautionary tale there. That's technically it, right? Now, the only other thing you could have done, potentially, to simplify further, would be if you had terms which could be factored further, you could factor them and cancel if possible. But for example, if this was 3x minus 6 instead of 3x minus 2, I might factor out that 3, right, and see if anything cancels. But that's not possible in this case, so I'm finished. Be careful here. You can't just cancel through the x's because you see x on top and x on bottom. That's because you have different terms, and you can never cancel through different terms. Finally, the domain does have a new restriction, doesn't it? Yeah, that 2x plus 1 can never equal 0. So that would mean that 2x can never equal, when you subtract there, negative 1, so that x can never equal negative 1 over 2. How would you have written that domain? Did you do it correctly? Any number to the left of it's okay, so negative infinity to negative 1/2 parentheses, meaning you can't include it, or any number to the right of negative half is okay. Negative half in parentheses to infinity. So make sure you practice interval notation. That might be a skill that you need some practice with. Also, feel free to check out the Desmos link to see these graphs and make more sense of what's going on, especially because our next video will be us using function notation to go over graphs of functions. So, okay, we've done a lot. That's a lot of content. I hope you will take time to pause this video, go back and retry all the different topics that you need practice on, and remember to practice it because math is not a spectator sport. I'll see you next time.